urgent. In a high-stakes mining operation, a multi-million-dollar machine suddenly grinds to a halt in the middle of a shift. When the dust settles, engineers do what they are trained to do. They log the failure into their ERP or CMMS database to build up their historical data. But relying exclusively on past data creates an epistemological trap. If you only look at history, your maintenance strategy is completely reactive. This methodology leaves massive operational blind spots. You leave the fleet wide open to unmitigated failures that haven't happened on your site yet. Historical logging is essentially forensic archaeology. It tells you what killed the machine yesterday, but it does nothing to engineer a system that will survive tomorrow. To prevent these catastrophic breakdowns, heavy industry relies on a standard protocol, failure mode and effects analysis, or FMEA. Yet operations face a persistent paradox. Teams spend thousands of hours documenting FMEAs, but fleets still suffer from low mean time between failures and unscheduled downtime. The tool itself is structurally sound. The problem lies in widespread misconceptions about how to apply its methodology in the field. FMEA is designed to be a proactive architectural weapon. It must be deployed long before a piece of equipment ever touches the dirt. To actually optimize fleet availability, reliability teams have to aggressively expand their predictive data horizons, master the limits of risk scoring, and rigorously close the mitigation loop. The absolute first step of a proper FMEA is defining strict operational boundaries. You have to isolate the exact system you are analyzing, otherwise the scope becomes unmanageable. Next comes the functional breakdown. You cannot identify how a component fails if you haven't first defined its precise normal function. This requires a cross-functional team. Planners sitting behind a desk must bring in subject matter experts, the senior mechanics and equipment operators who know how machines actually behave in the pit. To fix the data deficit and predict local failures before they strike, teams must combine their historical CMMS logs with external intelligence. That means digging into OEM manuals and troubleshooting guides to map out factory-warned operational limits. It means harvesting similar equipment history to anticipate breakdowns that have plagued parallel machines, even if the target unit has a clean record. And for completely novel failure modes, it requires integrating standard global reliability databases like ARETA, which compile worldwide industry failure rates. A rigorous FMEA synthesizes this multi-source intelligence to predict the future. It actively seeks out potential faults rather than passively waiting for historical proof. Once the failure modes are mapped, the analysis moves to the mathematical core of the AIAG or SAE J1739 standards, calculating the risk priority number, or RPN. The baseline formula yields the total risk score, aiming for a maximum of 1,000. Severity assesses the physical impact on a scale of 1 to 10. Occurrence measures the frequency of the root cause happening. Detection requires an inversion of logic. For detection, 10 is the worst. The fault is impossible to detect. 1 is optimal. The system catches the problem automatically. This reverse logic exists because early warning sensors allow for human intervention. Catching a catastrophic problem early significantly drops the functional risk. Cautionary. Multiplying these three variables yields a clean numerical score. But treating this pure math as an absolute, unquestionable truth is a dangerous pitfall. Consider a theoretical edge case where the math produces an extremely low total RPN of just 10. An occurrence of 1 means the event is almost impossible. Multiply that by a detection of 1, indicating perfect automatic warning sensors. The hidden, dangerous variable here is a severity score of 10, representing a catastrophic, life-threatening hazard. This document outlines an absolute mandate, the severity override. If the score reaches 9 or 10, total RPN math is discarded and the failure escalates. For example, a catastrophic haul truck fire requires mandatory secondary braking and fire suppression. Mathematical probability never outweighs human life. Extreme severity dictates multi-layered physical interventions, regardless of statistical unlikelihood. After the assessment phase, teams are left with a chaotic, unsorted mass of calculated failure modes and raw RPNs. To cut through the noise, you have to sort the data and ruthlessly apply the Pareto principle, the 80-20 rule. Targeting the maintenance budget solely at the top 20% of the highest RPNs resolves 80% of unscheduled breakdowns in the pit. Operations use an internal risk matrix for actionable thresholds. Critical risks scoring between 500 and 1,000 mandate grounding the equipment, like fixing a steering defect. High risks between 250 and 499 demand immediate prioritization, like flushing an excavator's hydraulic pump. These prioritized risks carry an administrative mandate. The team must assign a specific preventative action, a strict deadline, and a designated person in charge. Finally, once the new maintenance interval or part upgrade is implemented, the risk must be verified. You calculate the residual risk by running the RPN formula again. An FMEA is useless as a static document. If the assessment does not force a physical change verified by a lowered residual risk, it is merely a paperwork exercise. This animated cycle maps the complete proactive framework, replacing the reactive timeline with a dynamic predictive loop. FMEA operates as a continuous engineering protocol, constantly adapting to new data and changing operational realities. Integrating global databases with cross-functional field intuition permanently defeats the historical data trap. The severity override guarantees that catastrophic safety hazards never slip through loopholes in probability math. And the ultimate success of the system is proven on the ground by executing physical maintenance changes verified by lower residual risk scores. The operational result of this rigorous protocol is fully secured safety, eliminated unscheduled downtime, and maximized heavy fleet availability. Elite maintenance teams do not pride themselves on reacting to breakdowns quickly. They use FMEA to systematically engineer the probability of failure out of existence.